The effects of any charge distribution can be described either in terms of electric field or in terms of electrical potential. Electrical potential is often easier to use because it is a scalar, whereas electric field is a vector. So there is an intimate connection between the potential and the field. So let us consider the case of a uniform electric field, such as the field between two parallel plates. So if I have a positively charged plate and a negatively charged plate, and let's assume there is a potential difference between the two plates, which I name it as VBA, or you can just say potential difference as VBA. And this generates a uniform electric field between the two plates. So the difference, as we already know, the change in the potential difference, which is VBA, you can write VBA or you can write delta VBA because it's easier to relate to delta meaning change, but your textbook has kept the potential difference as VBA, indicating it's a change. Either one is fine. So your work done, we already know, is equivalent to change in potential difference over Q, following the same formula that change in potential difference BA is minus of work done over charge, which in other words can be, if you have to find the work done, you can use this approach. So work is also force multiplied by distance. We found that in the previous section, we learned that work done is force into distance, and this being the electrical force, because electrical field, magnitude of electrical field is magnitude of electrical force over charge, and in other words, magnitude of force is Q into E. So if we compare equation 1 and equation 2 and set them equal to each other, so we will have QED is equivalent to minus Q of change in potential energy, a potential difference between B and A, two electrodes. So if you say B and A, if you see that the charge and charge cancels out, the D is the distance of separation. So let's use small case for that. And this will help you get the electrical field. So the electrical field has another formula, which is minus change in potential difference over the distance of separation between the plates. In the earlier parts, we learned that electrical field is force per unit charge. There's a different formula for electrical field also now, which defines electrical field as minus change in potential difference over the distance of separation between the plates. So these two are used independently as the scenario approaches, but the electrical field in this case has the unit of Newton per Coulomb, and in this case we have another unit of electrical field, which is volts per meter. Hence 1 volt over 1 meter must be same as 1 Newton over 1 Coulomb. Both set of units are used interchangeably depending on which equation you are using. The minus sign that you see in the other equation tells us that electrical field points in the direction of decreasing potential. Let's take the example of from your textbook, and we find out what potential difference is needed to stop an electron that has an initial velocity of 6 cross 10 raised power 15 meters per second. Now, we just learned that the delta V of BA, which is the electrical potential difference, is equivalent to minus work done over the charge. If you have to find the electrical potential difference, this work done is also electrical potential energy over Q. So what potential difference is needed to stop an electron that has an initial velocity of 6.0 cross 10 raised per 5. So your job is to first find out what's happening in this scenario. The object is moving, the charge is moving, energy is conserved. So first thing, energy is conserved. Change in potential energy is equal and opposite to change in kinetic energy. So we use this principle, or in other words, we can say change in PE plus change in KE is equivalent to 0, which is the conservation of energy that we had learned in mechanics. So using this principle that change in PE will be equivalent to minus times KE, we can therefore modify this equation, and instead of writing PE, we can write minus times minus change in KE over the charge. But KE is, we know that KE is 1 by 2. Kinetic energy is 1 by 2 mv square. If we assume that it started initially at, the electron has an initial velocity, V naught is 6.0 cross 10 raised per 5 meters per second, and the final velocity is 0. So you can find the change. So delta VBA is minus times minus, it makes it plus KE over Q, but change in KE will be final potential and kinetic energy minus initial kinetic energy over Q. If you look at this equation, the final kinetic energy is 0. So therefore, your delta VBA, which is the change in potential difference, or the potential difference, is minus 1 by 2 mv naught square over Q. Your ultimate answer will be negative. So go ahead and substitute these values and show all the work needed. Mass of the electron, we are moving an electron, so you should know what the mass is, 9.11 cross 10 to the power of minus 31, and the initial speed that's already given as 6.0 cross 10 to the power of plus 5 meters per second, and whole divided by the charge of the electron, magnitude of the charge, or minus 1.6 cross 10 to the power of minus 19 coulombs. So once you work on this, you should end up getting your entire energy potential difference as .025 volts, or if you follow the 2 sig fix, that should be 1.0 volts only. Okay. The next part, we learn further about the relationship between electrical potential and electrical field. And in here, we already found out that delta VBA is minus E times T. We found the new equation. If we go back and see what we learned just now, between the two equations, we found E is equivalent to minus delta VBA over T, right? So keeping that in mind, this equation is only true for uniform electrical fields, and in general, the electric field in a given direction at any point in space is equal to the rate at which the electrical potential decreases over a certain distance, or the distance in that direction. This is the general relation between E and V, And in a region where E is not uniform, the connection between E and V takes on different paths. And in general, it is possible to show that electrical field in a given direction at any point in space is equal to the rate at which the electrical potential decreases over a certain distance. So if we have a 3D vector for the electrical field, so if we have E is equivalent to E vector, which is made up of X vector component, Y vector component, and Z vector component, the overall vector in a uniform field is shown as in the X direction, it will be change in voltage or potential difference in the X direction. So that is delta X. If we keep the minus out, we can write delta V over delta Y plus delta V over delta Z. So this is the general representation of the formula that you just found, that minus VBA, the minus sign kept outside. So if you are breaking the electric field into three components, you can also represent EX, EY, and EZ in these different forms. One important part about electrical field is when a very high voltage is present, air can become ionized due to high electrical fields. That's what happens in auroras as well. Any free electron can be accelerated to sufficient kinetic energy to knock the electrons out of oxygen and nitrogen molecules in the air. This breakdown of air occurs when electrical field is greater than, if electrical field is greater than 3 cross 10 to the power of 6 volts per meter, the air can break down. When electrons recombine with their molecules, light is emitted, and that's why you see these auroras and all. Such breakdown of air is the source of lightning, the spark of a car spark plug, and even short sparks between your fingers and the doorknob after you walk across a synthetic rug or slide across a car seat, which is not significant enough compared to what a lightning bolt generates. So we can go ahead and work on one more problem in this direction. An electrical field of 525 volts per meter is desired between two parallel plates. So we have two parallel plates, one positive, one negative, telling us this is a uniform electrical field. The distance of separation between them is 11 millimeters. So the electrical field is directed from plus to minus. So we know the direction of electrical field. How large a voltage should be applied between the two plates? How much voltage should we apply between the two if we want to maintain an electrical field of 525 volts per meter? So your E is given as 525 volts per meter. The distance of separation is 11.0 mm, which is millimeters. Convert them right here. So D is given, E is given, and you can use the other form of the potential difference or the electrical field, where we know electrical field is equivalent to change in voltage or change potential difference between two plates over the distance of separation. It's because of this we get volts per meter as the unit. Remember, electrical field is also force per unit charge, which gives us Newton per coulomb. So volts per meter is always going to be the same as newtons per coulomb. So depending on which formula of electrical field you are using, you will use the unit SI unit accordingly. So in this case, we are using voltage over or potential difference over distance, and we'll use the unit as volts per meter. So we have to, how large a voltage can be maintained? So we have to find delta VBA. delta VBA will be equivalent to E multiplied by D, the magnitude of the voltage. So your electrical field is 525 volts per meter, and the distance of separation is 11.0 cross 10 to the power of minus 3 meters. And you can go ahead and see how much of the voltage this generates or is needed to keep this kind of electrical field intact. And the unit of potential difference is always going to be volts, which you can see from here. We end up getting volts in here. We can further work on another problem from your textbook. The electrical field between two parallel plates connected to a 45-volt battery is 1900 volts per meter. How far apart the plates are? So again, in this case, if you have two parallel plates, and if the electrical field is 1900 volts per meter, and the potential difference delta VBA is 45 volts, we need to find out what distance of separation will be required to maintain this electrical field. So your job is to find D in meters. Again, a very simple problem using the same concept of electrical field is equivalent to change in potential difference over the distance of separation. So therefore, distance of separation is change in potential difference over D over your electrical field. So go ahead and substitute the values that you have. 45 volts over 1900 volts per meter will end up giving you the distance. Of course, it's going to be a small distance, and that's why it's going to be in millimeters. So once you work on this, you should end up getting 2.4 cross 10 to the power of minus 2 millimeters, or minus 2 meters, or 0.24 millimeters. So that's a very small distance. Again, let's work on problem number 12. What is the speed of an electron with kinetic energy 850 electron volts, or 0.50 kilo electron volts? So this is a problem which talks about the conversion of joules into electron volts. So 1 electron volt has an equivalent in joule. 1 electron volt is the unit of energy. It's not the unit of potential difference. So we'll have to bear that in mind. So the joule is a very large unit for dealing with energies of electrons, atoms, or molecules. For this purpose, we have 1 electron volt, which is used. And 1 electron volt is defined as the energy required or acquired by a particle carrying a charge whose magnitude equals to the charge of an electron. So that's why we call it moving through a potential difference of 1 volt. So the charge on electron, as we already know, is minus 1.6 cross 10 to the power of minus 19 coulombs. If we take the magnitude of the electron charge, we can use the positive sign, 10 to the power of minus 19 coulombs. And we say 1 electron volt. So the change in potential difference is 1 volt. So if we have to find 1 electron volt, that's going to be 1.6 cross 10 to the power of minus 19 coulombs multiplied by 1 volt. And that's nothing but joules. So it's 1.6 cross 10 to the power of minus 19 joules, because it's the unit of energy. So here you are converting 850, you're finding the speed of an electron with kinetic energy 850 electron volts, and you can also convert it to joules if you want to. So part A is for 850. We know 1 by 2. mv square is the kinetic energy, and therefore V is equivalent to square root of if you rearrange 2 times kinetic energy over m. In your case, it's we have been given 850 electron volts, so that will be square root of 2 times 850 electron volts. But instead of writing electron volts, we can represent it in terms of joules by multiplying it by joule. That's converting it joules, and this is electron volts and this is electron volts. So you can see the unit conversion is happening, although we could have done it before. Converting 850 electron volts to joules is fairly simple. 850 electron volts, 1 joule over 1 electron volt. So 850 electron volts is 850 joules. Okay. So divided by your mass of the electron, which is 9.11 cross 10 to the power of minus 31 kgs. And we end up getting the speed as 1.7 cross 10 to the power of 7 meters per second. That's a very high number. And you follow the same procedure for 0.50 kilo electron volts, which means it's 0.50 cross 10 to the power of 3 electron volts, definitely higher. So if you follow the same math and put 1 by 2 mv square is equal to change in kinetic energy, and then go ahead and put the energy as 150.50 into 10 to the power of 3 electron volts. That's also going to be in joules, the same number in joules. You will end up getting 1.3 cross 10 to the power of 7 meters per second. So number 13 is finding what is the speed of proton whose Ke is 4.2 kilo electron volts. So these are basically based on converting from 1 electron volts to joules. So again in here, instead of an electron, we are talking about proton. Mass of the proton is 1.67 cross 10 to the power of minus 27 kg, and the magnitude of the charge for proton will stay the same as electron. So Q of proton 1.6 cross 10 to the power of minus 19 coulomb. It does not change. So what is the speed of the electron? We convert the 1 by 2 m mass of the proton, velocity of the proton square, must be equivalent to change in Ke. So the change in Ke is given as 4.2 kilo electron volts, which is also 4.2 cross 10 to the power of 3 cross 1.6 cross 10 raised to power minus 19 joules, because 1 electron volt is 1.6 cross 10 raised to power minus 19 joules. And then we can go ahead and find the velocity by rearranging the terms. Your v will be square root of all of this, 4.2 cross 10 to the power of 3 cross 1.6 cross 10 raised to power minus 19 joules, whole divided by your mp, which is the mass of the proton. So we can substitute the mass of the proton as 1.67 cross 10 to the power of minus 27 kgs. Go ahead and work on the numbers after plugging them in, and you'll see that the speed of the proton comes out to be 9.0 cross 10 to the power of 5 meters per second is the speed. So this is how these problems can be done.